anomalous spin wave excitation in helical magnet. My name is Shin Miyahara from Fukuoka University. This is outline of my talk. First, I introduce magnet-electric effect. And today, I would like to convince you that magnetic excitation in helical magnet show anomalous features. Finally, I conclude my talk. In conventional materials, electric polarization can be tuned by external electric field, and magnetization can be tuned by external magnetic field. In multiferroids, there is a strong coupling between electric polarization and magnetization. Due to the coupling, sometimes electric polarization can be tuned by external magnetic field, and magnetization can be tuned by external electric field. So there is a cross correlation. One of the typical mechanisms of the magnet-electric coupling is a spin current mechanism. Here, the electric polarization couples to pair of spins. Electric polarization due to the spin current mechanism is given in this form. And here, the electric polarization coupled to the anti-symmetric spin pairs. When the non-collinear spin structure is realized, electric polarization perpendicular to the bond appears. So due to such a kind of spin current mechanism, cycloidal spin structure can couple to the electric polarization. When we consider AB cycloidal plane, then the polarization, electric polarization appears to A direction. For the BC cycloidal plane, electric polarization appears to C direction. So in that sense, by changing the cycloidal plane direction, we can control the direction of electric polarization. Such a kind of cloaking can be observed in the experiment. This is the case for R Magna 03, whose ground state is a cycloidal spin structure, AB cycloidal spin structure. So in that sense, without external magnetic field, electric polarization aligned to A direction appears. In this material, by applying the magnetic field to A direction, at that field, there is a cycloidal plane props. So cycloidal plane props from AB cycloidal to BC cycloidal. And at the cloaking point, we can observe also the electric polarization flow. So in that sense, the direction of the electric polarization changing from A to C in this way. Magnet-electric coupling induce anomalous feature even in dynamical process of the magnetic excitation. So due to the coupling, some oscillating electric field can induce modulation of the magnetic structure and sometimes which couple to the magnetic excitation. So in that sense, in the multiferrous materials, some of the magnetic excitation can be excited by oscillating electric field. We call such a kind of electroactive magnet as electromagnet. This is an example of the observation of the electromagnetic process. Even in the helical magnet, we can expect electromagnet. In helical magnet, electric polarization within the cycloidal plane appears. So in that sense, by applying oscillating electric field perpendicular to the cycloidal plane, we can really modulate the electric polarization. That is the cycloidal plane. So such a kind of oscillation of the cycloidal plane coupled to the magnon excitation. So in that sense, by applying the oscillating electric field perpendicular to the cycloidal plane, we can excite some magnon excitation. Purpose of my talk is to clarify the feature of electroactive magnetic excitation, so-called electromagnon in helical magnets. To clarify the electromagnon in the helical magnet, we consider frustrated Heisenberg J1, J2. Here, this is a model, and nearest neighbor coupling is J1, and next nearest neighbor coupling along y direction is J2. At certain parameter range, cycloidal ground state realized in this model. By applying the spin wave theory, we can calculate magnon dispersion, and this is the case for this parameter set. So we consider some J1, J2 Heisenberg model, and as a coupling between electric polarization and magnetic structure, we introduce spin current electric polarization induced by the spin current mechanism. So in this form, to obtain the excitation, magnetic excitation, we can apply spin wave expansion to magnetization and electric polarization induced by spin current mechanism, and we can get this formula. So in that sense, here M magnetization and electric polarization coupled to the plus minus Q0 magnon. So in that sense, in this model, plus minus Q0 magnon are both magnet and electroactive mode. So this is a magnon dispersion. So in that sense, plus Q0 and minus Q0 mode clearly coupled can be excited by oscillating magnetic and electric field. Since both magnetic field and electric field can excite magnon excitation, we can expect some cross correlation even in the dynamical process. And such a cross correlation can be observed as non-reciprocal directional dichroism. That means absorption of the linearly polarized light strongly depend on the propagation direction of light. So this is the absorption question at certain magnetic field perpendicular to the cycloidal plane. And red light is a K absorption question for the light propagating to plus y direction. And blue mark represents the result for the light propagating minus y direction. So this peak corresponding to the lower magnon mode, in this case plus Q0 mode, and higher mode corresponding to the higher mode. In that sense, that is corresponding to the minus Q0. And absorption strongly depends on the direction of the light. And such non-reciprocal directional diagram was observed even in the experiment. And this is the experimental result in R1 and O3. And this mode corresponding to the higher mode in our calculation, and which shows strong non-reciprocal directional diagrams as we observed, as we expected in the theoretical calculation. And this is consistent with our calculation. Finally, we consider the spin wave spin current in helical map. So we treat the J1, J2 model and solve the LLG equations by using a numerical calculation. And we consider two-dimensional model and applying some oscillating magnetic field at the center of the plane. And check the way of the propagation of the spin waves. These are the results. Left is the case. The external magnetic field is zero. In the helical magnet, right propagation spin wave and left propagating spin wave are identical. Right is the case. We apply static magnetic field perpendicular to the cycloidal plane. Here, spin wave propagate to the right direction. The way of the propagation under the magnetic field can be controlled by the direction of the external magnetic field. The left panel is the case. We apply the external static magnetic field to plus G direction, and right panel is the case. Apply the external magnetic field to the minus G direction. In the left, spin wave can propagate to right direction, and in the right panel, spin wave can propagate to the left direction. So in this way, the way of the propagation of the spin wave can be tuned by external magnetic field. So this is conclusion of my talk. We can show that the spin wave excitation in helical magnets show anomalous features. Thank you for your attention.